Welcome, everyone, to this explainer on 5G foundations. Today, we are kicking off Phase 1 of our 5G learning module, and we're looking at a pretty massive paradigm shift in telecommunications. Basically, we're moving from a world that's focused almost entirely on connecting people to a world built to connect absolutely everything. So before we get bogged down in the dense technical specs, I want you to ask yourself, what does a truly connected smart factory or a fully integrated smart city actually require to function? It's not just about downloading a movie faster on your phone. It's about flawlessly orchestrating millions of sensors, autonomous vehicles, and industrial robots, all in real time. That is the grand vision of 5G. Here is our agenda for today's module. We are going to cover 1. The 5G revolution. 2. The 3 pillars of 5G. 3. Measuring success with 5G KPIs. 4. High-level 5G architecture. 5. Virtualization. And finally, 6. Labs and assessment. Let's jump right into Section 1, the 5G revolution, connecting everything. It's really helpful to ground ourselves in the historical context here. Think about where we started with basic 1G analog voice and how we evolved all the way through to 4G, which, of course, gave us robust broadband voice and data. But here's the thing. 4G was still largely about us, the human users. 5G acts as the digital backbone for Industry 4.0 and massive automation. We are shifting the focus entirely toward the Internet of Things. Section 2, the 3 pillars of 5G, eMBB, URLLC, and mMTC. Let's deconstruct the actual what of 5G. The International Telecommunication Union, through their IMT 2020 vision, identified 3 major usage scenarios. These 3 foundational pillars have to operate side by side because 5G is engineered to handle completely different markets simultaneously. Everything from streaming an 8K video on your laptop all the way down to managing the precision of factory robots and smart city traffic lights. First up is MMB, or Enhanced Mobile Broadband. This one is essentially a straightforward evolution of what we already know from 4G, just totally supercharged. It's designed to deliver an increasingly seamless user experience with extreme data rates. We are talking targets of at least 50 megabits per second outdoors everywhere, and a whopping 1 gigabit per second indoors. This is the pillar that makes augmented and virtual reality plus Ultra HD video streaming completely seamless. Next, we have URLLC. Ultra-reliable and low-latency communications. Honestly, this is arguably the most revolutionary pillar for enterprise and industry. It provides the absolute zero margin of error connectivity required for critical control. We are talking about sub-millisecond end-to-end latency coupled with greater than 99.9999% reliability. It is literally the bedrock for wireless control in industrial manufacturing, autonomous vehicle safety, or even remote medical surgery. And then there's mMTC, or Massive Machine Type Communication. So while eMB goes for pure speed and URLLC goes for instant response, mMTC is all about immense scale. It relies on highly efficient signaling designed to support a massive volume of devices that typically just transmit very low volumes of non-delay sensitive data. This scales up to support the billions of sensors and actuators that form the nervous system of things like smart agricultural monitoring and city infrastructure. Moving on to Section 3, Measuring Success, IMT 2020 5G KPIs. To ensure all 3 of these totally distinct pillars can function on the very same network, we have to measure them against some incredibly strict key performance indicators. 20 gigabits per second. Just let that sink in for a second. The peak data rate target for IMT 2020 jumps to a staggering 20 gigabits per second. To put that into perspective, that represents the absolute theoretical ceiling of what the 5G radio interface is required to handle for download. When we stack these targets directly up against LTE, it's a whole new ballgame. 5G demands up to a 10-fold increase in capabilities across the board. Latency? That drops from 10 milliseconds down to just 1 millisecond. Connection density explodes from 100,000 devices per square kilometer in LTE to an astounding 1 million devices per square kilometer in 5G. And of course, that peak data rate leaps from 1 gigabit to 20 gigabits per second. Section 4, High-Level 5G Architecture, RAN, Core, and Deployment. So the million-dollar question is, how do we physically and logically build a network to actually hit those massive KPIs? Well, let's look at the deployment migration paths operators take. In a non-standalone architecture, or NSA, you anchor the new 5G radio, the GNB, to your existing 4G evolved packet core. It's a fast-to-launch option relying on dual connectivity. However, to unlock the true magic of 5G, like network slicing and URLLC, you eventually have to move to the standalone option, or SA. In SA, the 5G radio connects natively and directly to the new 5G next-generation core. Diving deeper into that 5G core, we hit a totally new paradigm called a service-based architecture, or SBA. Unlike legacy telecom cores that were built on dedicated, clunky physical appliances, this is composed entirely of independent software network functions. You have entities like the AMF, handling access and mobility management, and the SMF, handling session management. These are self-contained, independent software units that can be scaled flexibly in the cloud. A foundational principle making all this flexibility possible is CUPS, control and user plane separation. In previous generations, control signaling and user data routing were completely tangled together. 5G untangles them. The control plane functions, like the AMF and SMF, manage the rules and connections. Meanwhile, the user plane function, the UPF, handles the actual data forwarding. By separating them, we can drop user plane resources right at the edge of the network, as close to the access point as possible, to drastically slash end-to-end latency while keeping the control centralized. Section 5. Virtualization and Enabling Technologies. Implementing a service-based architecture with separated planes requires a complete departure from dedicated hardware. By virtualizing the network, 5G utilizes cloud-native deployment principles and software-defined networking. And because everything is virtualized software now, we can use network slicing. Slicing lets us create multiple, customized, logical networks on the exact same physical infrastructure. So one slice could be tailored for high-bandwidth eMBB, while another slice on that same hardware is strictly prioritized for low-latency URLLC. Now, here is a real game changer for enterprise applications: mobile edge computing. The edge cloud allows processing of huge amounts of data right where the traffic is generated. This is absolutely mandatory. If we are going to support sub-millisecond URLC use cases, like instant video analytics in a private factory, we simply cannot afford the round-trip time it takes to send data back and forth to some distant, centralized server. Keep the processing local, keep the latency low. And finally, Section 6, next steps, hands-on labs and assessment. Theory is great, but getting your hands dirty with the technology is where true understanding actually happens. For your practical assignment, you will be spinning up open-source tools to build a minimum viable product private 5G network. You'll deploy free 5GC or Open 5GS cores alongside SRS RAN radios on containers. You're going to run simple throughput demos, capture signaling traffic using Wireshark to really see how devices attach, and we'll dive into some rigorous case study discussions comparing this open-source build approach versus a commercial carrier-grade buy solution. To wrap up Phase 1, I'm going to leave you with a quick brain teaser to lock in today's concepts. Which of the 3 5G pillars requires sub-millisecond latency and edge computing to function? Think back to the usage scenarios we discussed, those incredibly strict KPIs, and how edge computing enables those fast reaction times. Lock in your answer, review your notes, and I will see you in Phase.
Welcome back, class. Today, we're diving right into Phase 2 of our Enterprise Learning module. In this explainer, we're going to unpack the anatomy of 5G architecture, and we're going all the way from the macro-level network design right down to the microscopic math of the physical layer. Now, if you're looking at this from an enterprise review board perspective, your core learning objectives today are pretty straightforward. We need to compare architectures, identify major network functions, explain virtualization, and ultimately map all these technical concepts directly to actionable deliverables for real-world network deployments. Here's a quick look at our syllabus for today. We'll start with deployment architectures, move inside the 5G core, disaggregate the radio access network, look at 5G numerology, and then wrap things up with deploying and scaling. Let's get into it.
All right, Part 1, Architectures, NSA versus SA. Let's look at the big picture of how we actually deploy this network.
So I want you to think about this critically from a business perspective for a second before we even look at the technical models. When you're launching a massive, capital-intensive technology like 5G, time to market is literally everything. I mean, why wait years to build a brand new core when you can just leverage the infrastructure you already have? That brings us to our 2 main deployment models. Early rollouts heavily relied on the non-standalone, or NSA architecture. This is option 3.
Basically, it anchors the control plane, the signaling and management, to the existing 4G LT evolved packet core, while simply adding 5G and R radios to boost the user throughput. Then you have standalone or SA. This is the end game, folks. In SA, the 5G radio connects directly to the new 5G next-gen core, which unlocks the full native capabilities of the network.
To summarize the strategic trade-offs for your enterprise deployments, NSA gets you to market way faster by piggybacking on the evolved packet core. But standalone? That is the ultimate destination to realize a true service-based architecture. SA is absolutely crucial because it's what gives you access to advanced enterprise features, like true network slicing and voice over 5G.
Moving along, let's zoom in and examine the brain and organs of that new 5G core.
Okay, I know this looks like a massive alphabet soup of network functions. To help you memorize these for your assessments, think of the 5G core as a corporate office building. The AMF is your front desk and security. It handles user registration and mobility. The UDM? That's human resources, storing all the subscriber profiles and security keys. The SMF is session control, setting up your connections. The UPF is the shipping department, routing the actual user data packets. And finally, the PCF is your policy enforcement, making sure everything meets quality and charging standards. Let's actually trace a standalone access registration call step by step so you can see how these departments communicate in real time. And by the way, this is exactly the kind of process you'd monitor in a lab environment using a packet capture tool like Wireshark. So first, the user equipment sends a registration request to the AMF. The AMF then talks to the UDM to authenticate the user. Once they're authenticated, policies are pulled from the PCF. And finally, the SMF sets up the data tunnel right through the UPF. Notice the specific backend interaction during that authentication phase. The unified data management function plays a really critical role here. It interacts with the authentication server function to generate and provide the actual authentication vectors needed to securely verify our user equipment. It is a highly secure, completely automated handshake.
Section 3. Moving from the core out to the limbs of our network, let's talk about the radio access network. Specifically, we need to look at the GNB-CU/DU split. In legacy networks, a base station was basically a monolithic piece of proprietary hardware. But 5G standardizes a split, dividing the base station into a central unit and one or more distributed units, connected by what's called the F1 interface. This disaggregation is an absolute game changer. It fundamentally enables cloud-native virtualization and Open RAN right at the edge.
The crucial point here is understanding what goes where. By placing the latency-critical, real-time protocols, like the MAC and PHY layers, in the distributed unit close to the antenna, and centralizing the higher, less time-sensitive layers in the central unit, operators can heavily leverage general-purpose cloud computing. This massively streamlines hardware costs and allows for incredible scalability. Case in point, this is exactly how industry leaders like Rakuten and their cloud-native 5G telco rollout are operating in the real world.
All right, let's pull out our microscopes for Section 4. We're going to examine the physical layer math, known as 5G numerology.
This is where 5G gets its incredible flexibility. Unlike 4G LTE, which was basically stuck at a rigid 15 kHz subcarrier spacing, 5G supports a highly flexible OFDM numerology. It scales proportionally from 15 kHz all the way up to 240 kHz, and it adapts the cyclic prefix as it goes to maintain signal orthogonality.
So, what does this mathematical scaling actually do to transmission time? Well, because of this proportional math, there's an inverse relationship with time. As our subcarrier spacing gets wider in frequency, our slot duration drastically decreases in time. It shrinks from a full 1 millisecond at 15 kHz down to just a tiny fraction of a millisecond at 240 kHz. A classic problem-solving assessment for your lab reports will be to calculate this exact slot duration change, so definitely keep this relationship in mind.
This mathematical flexibility also allows for the creation of mini-slots. Instead of waiting for a full slot boundary to transmit, a device can just fire off data in 2, 4, or 7 symbols. This is absolutely essential for reducing transmission delays in mission-critical enterprise applications. Think about real-time robotic control in a smart factory. Mini-slots are what fulfill that promise of ultra-reliable low-latency communication.
Finally, Section 5. Let's take everything we've learned today, from the core architecture to that physical layer math, and apply it to a real-world deployment strategy. This right here is the classic build versus buy dilemma. Every engineering team and enterprise review board has to confront this when charting their migration path. How do you start testing these capabilities, building a minimum viable product without breaking the bank while still planning for a robust, scalable future?
Well, for an instructional lab or an MVP, you might spin up open-source tools. Things like Free5GC or Open5GS on a Kubernetes cluster may be paired with SRS RAN for your GNBs just to test the waters. It's low cost, it's highly innovative. But you have to contrast that with a highly reliable, integrated carrier-grade system from vendors like Ericsson or Nokia. That carrier-grade reliability becomes crucial when you start discussing the strict service-level agreements required for, say, a full-scale production-ready smart factory.
Ultimately, your goal is to map a strategic migration path. You need to outline exactly how your enterprise will transition from an experimental, non-standalone 4G to 5G integration into a fully resilient 24/7 cloud-native standalone network. This requires deep thinking about your CI/CD pipelines, virtualization scalability, and understanding how the 5G core's separation of control and user planes guarantees that much-needed reliability.
So, as network slicing and virtualized edge computing become the new standard, how will your enterprise bridge the gap between open-source agility and carrier-grade reliability? I'll leave you to ponder that vital question as you review your own network blueprints and learning objectives. Bridging that gap is the absolute key to unlocking 5G's true potential for digital transformation. Thanks for joining today's Explainer. Class dismissed.
Phase 3 of our enterprise module, the 5G NR Protocol Stack Masterclass. If you've been following along, you know we're moving from the high-level architecture down into the actual nitty-gritty mechanics of how data literally flies through the air interface. For those of you tasked with building out enterprise proofs of concept, maybe you're spinning up a free 5GC core or deploying an Open RAN setup in a smart factory, mastering these layers is absolutely critical for your scalability and resilience strategies. Here's our game plan today. We'll quickly hit our learning objectives, map out the 5G protocol stack, dive into SDApp and QoS mapping, and then work our way down through the user plane lower layers. After that, we'll cover RRC states, and finally, we'll wrap up with 5G numerology and channels. Section 1, Phase 3 Learning Objectives. By the end of this masterclass, here's what you really need to take away. You must be able to clearly explain each layer of the NR air interface for both the user and control planes. You need a solid grasp on how quality of service flow mapping works, especially with the brand new SDAP layer. You'll also need to be able to describe the RRC unactive state and why it's such a game changer for battery life. And finally, you must understand 5G numerology and the trade-offs that come with flexible subcarrier spacing. We're going to be testing all of this through problem-solving quizzes and your lab reports on Wireshark captures later on, so definitely take good notes. Okay, moving right along to Section 2, the 5G protocol stack. Let's visualize the actual flow of data between the user equipment and the G node B. When we look at the stack, right at the top you'll spot SDAP. That is our brand new layer in 5G. Below that, we have PDCP, RLC, MAC, and finally the physical layer, sitting at the absolute bottom. As IP packets come in at the top, they get passed down through these layers, encapsulated with headers, segmented, multiplexed, and eventually turned into a transport block transmitted over the air. If you're running an open-source SRS RAN lab, this is the exact flow of data you'll be capturing and analyzing. Section 3, SDAP and QoS mapping. So the Service Data Adaptation Protocol, or SDAP, operates strictly in the user plane. And I really want to emphasize this point for the class. This protocol layer did not exist in LTE. It was introduced specifically because 5G handles quality of service fundamentally differently. Instead of relying on a super rigid one-to-one mapping of bearers from the core network like 4G did, 5G uses a much more flexible flow-based QoS model. And this flow-based model is brilliant. Imagine an enterprise VoIP call or a YouTube video stream coming through. The 5G core tags these specific IP flows with a QoS flow identifier, or QFI. Then the SDAP layer, which sits inside the GNB, acts as the ultimate traffic cop. It looks at those incoming QoS flows, say QFI3 and QFI4, and multiplexes them into a single data radio bearer, or DRB, over-the-air interface. The core network understands the strict service requirements, sure, but the radio network is fully entrusted to just map those flows efficiently over the air. Okay, so how does your phone or IoT device actually know how to send traffic back in the uplink? There are two ways this mapping happens. The network can explicitly configure the rules via RRC signaling. But the real magic of 5G is reflective QoS. With reflective QoS, the device simply observes the downlink packet's SDAP header. If it sees that a specific video flow came down on data radio bearer 1, it just reflects that rule using data radio bearer 1 to send its uplink video packets. This drastically cuts down on control plane signaling, which makes the whole network much more agile and scalable for enterprise deployments. Let's do a quick thought experiment to test your understanding of these architectural dependencies. Many operators and enterprises start their 5G migration by anchoring to their existing legacy networks. So what happens to this shiny new SDAAP layer if we deploy a non-standalone or NSA network that's still using a legacy 4G core? Well, it literally vanishes. The SDAP layer relies entirely on the 5G core to provide those flow-based QoS parameters. If you are using a 4G core in an NSA setup, it falls back to legacy bearer QoS, meaning the SDAP layer just isn't configured at all. This is absolutely crucial strategic context to keep in mind when you're deciding whether to build a quick MVP on NSA versus rolling out a full carrier-grade standalone 5G network.
Section 4. User plane lower layers.
Now, there's been a massive evolution in the radio link control, or RLC layer. In LTE, the RLC was responsible for ensuring packets were delivered in sequence to the higher layers, and it handled packet concatenation. But 5G NR strips those exact duties away from the RLC. Why? Latency. Waiting around in line to put packets in perfect order creates a real-time processing bottleneck. By pulling in-sequence delivery and concatenation out of the RLC, 5G can process packets incredibly fast, and that speed is non-negotiable for ultra-low latency enterprise applications. So if the RLC isn't doing it, who picks up the slack? The layer right above it, the PDCP layer, now handles that in-sequence delivery along with ciphering, integrity protection, and header compression. Below that, our newly streamlined RLC handles segmentation and error correction via ARQ. Then the MAC layer takes those logical channels, multiplexes them, handles HARQ retransmissions, and manages scheduling grants. And finally, the PHY layer translates the whole shebang into radio waves through OFDM coding, modulation, and beamforming. Section 5. RRC states and the control plane. 5G introduces a total breakthrough state called RRC_inactive. In legacy 4G, a device was pretty much either connected, which drains a battery, or idle, which saves battery, but requires a heavy, slow signaling process to wake back up. RRC_inactive is a brilliant middle ground. The UE context, meaning its security and routing information, is kept alive in the base station, but the actual radio bearers over the air are suspended. The crucial point here is that this solves a massive scalability problem. Think about an enterprise smart factory with 10,000 IoT sensors. They only send tiny bursts of data every now and then. By parking them in RRC inactive, we save their battery life and dramatically reduce signaling storms on the network. But because the base station still remembers them, they can resume their connection with lightning speed the moment they actually need to transmit. Section 6. 5G numerology and channels. In 4G, the distance between subcarriers on the radio grid was locked in at 15 kHz. 5G, however, introduces flexible numerology. The subcarrier spacing can scale all the way from 15 up to 240 kHz. But because of the fundamental math of radio frequencies, as you expand that subcarrier spacing, the duration of the slot shrinks proportionally. At 15 kHz, a slot takes 1 millisecond. But at 120 kHz, a slot takes a mere 0.125 milliseconds. To put that into perspective, that is roughly 2,000 times faster than the blink of a human eye. And get this, even with those drastically shorter slots, 5G pushes latency down even further using a concept called mini-slots. Normally, a device has to wait for an entire slot boundary, all 14 symbols, to finish before sending data. Mini-slots allow a device to hijack just 2, 4, or 7 symbols to instantly fire off critical data. This is the secret weapon for URLLC, or ultra-reliable low-latency communication, which is absolutely vital for keeping things like automated guided vehicles from crashing into each other on your factory floor. But quick word of warning, you can't just use any numerology for whatever you want. There are strict mapping rules. For instance, a subcarrier spacing of 240 kHz is extremely wide and fast, but it's not actually supported for regular data channels like the PDSEH or PUSHE. It is strictly reserved for synchronization signals. When you're designing your RF layout, understanding these limitations is essential. Okay, time for a quick pop quiz to test your memory and simulate our classroom assessment. Let's see who was paying close attention to our protocol stack breakdown earlier. Which layer performs packet segmentation but does not guarantee in-sequence delivery in 5G NR? It's the URLLC, or Radio Link Control Layer. Remember, dropping that in-sequence delivery requirement was a major architectural shift to optimize real-time processing, pushing that reordering responsibility right up to the PDCP layer. Before we wrap up, I want to leave you with a provocative engineering prompt for your next lab session. Based on this protocol stack, how would you design a 5G network slicing strategy that balances the need for ultra-low latency max scheduling using mini-slots while simultaneously adhering to strict SDOP QoS flow constraints from the core? Think about your build versus buy trade-offs here. Can an open-source MVP actually handle this, or does it require a carrier-grade managed service? Think on it, review your slides, and I'll see you in the next explainer.